I will begin with a word of prayer. Again. Here we go. Dear Father, I thank you again for these students. Just ask you to, again, just guide our steps today, Lord. In your name I pray. Amen. So let me just, if you can over here. So let's see here. Integral of c dx is cx plus c. Does that seem right? That seems kind of right, but we shouldn't use, I mean, you're assuming c was a constant. Good. That was my intention. But if we have that's a constant, then we should really add a different constant over here, like c2 or something, all right? Integral of x dx is x squared over 2 plus a constant. Yep, that'll work. Integral of the square root of x. Now, here there's some things missing, and this I will take off points for, but not on the card. But just, this is why we do this, is because it's a low pressure way for me to communicate to you that when things are missing, they're missing. Right? So this is not allowed. Like, we need an equality here, and there has to be an equality here, right? So not a big deal. I mean, it is kind of a big deal, but I'm happy that you have the right thing, is my point. Here we have, again, the equality is missing. 2, so that's 2x. Now, of course, this we could also express as 2 times the square root of x plus a constant. I wouldn't say this or that is to be, I mean, same answer. X to the n is, well, I would say yes, but this is a lowercase n, not an uppercase n. Nothing wrong with that. I'm just making it so I can see. So x to the n plus 1 over n plus 1. And this deserves a comment. What is that? What are we assuming about n? N is not equal to, yeah, right, exactly. N not equal to minus 1. And I see that was missing from my list. I will contribute something today to this list of antiderivatives. Well, these are not antiderivatives. These are what? These are indefinite integrals. What's the difference between an antiderivative and an indefinite integral? Well, maybe nothing. It depends on who taught you Calculus 1. All right, some people use these terms interchangeably. For me, the indefinite integral is the most general antiderivative. It's really a set of functions. That's why we have the plus c. It could be anything. I mean, the indefinite integral has to allow for all possible antiderivatives, whereas an antiderivative is just a specific function, which if you differentiate, you get back to the original function. All right, for me, that's the difference in terminology, but not everyone emphasizes that. Natural log the value of x plus a constant would be this indefinite integral, right? The n equals minus 1 case is special. We have that. Over here, integral of e to the x dx is e to the x plus a constant. That seems right on the money for me. It's good. Integral of a to the x dx is natural log. First of all, to be clear, I am assuming that a is positive, right? If a is not positive, if a is negative, I have no earthly idea what to tell you about those things. And this is not right. So the derivative of a to the x is the natural log of a times a to the x, right? But the integral of a to the x is, in fact, a to the x over the natural log of a, or you could, you know, various different ways to write it, but that's it. All right? Integral of sine is cosine. Does this seem right? No, it is not quite right. What is? Yeah, it's minus cosine, right? Remember that the ultimate judge of any alleged integral is if you differentiate the answer, you should get back to the integrand, right? If we differentiate cosine, we get minus sine. So there needs to be a minus there, because the derivative of minus cosine is minus a minus sine, which is sine. Integral of cosine is sine. Yep, that's good. Integral of sinh is cosh. So this is the hyperbolic sine, right? If you haven't seen this before, hyperbolic sine is, by definition, 1/2 e to the x minus e to the minus x. Hyperbolic cosine, cosh x as it's known, is 1/2 e to the x plus e to the minus x. I'll talk more about those in some other discussion, all right? That much I'll tell you right here, right now. We'll talk more about these later, all right? I know some of you haven't seen. Show of hands, who's never seen cosh and sinh in their previous calculus? See, you were cheated. You're supposed to see that in Calculus 1 here. Of those people who just raised their hands, how many people took Calculus 1 here? You never saw cosh and sinh in Calculus 1? Oh, you ran out of time? Oh.
These things exist.
Sprano.
Moving on.
Sprano. Oh, he told me that. I should remember. Anyway, it's not his fault. I mean, it's his fault. He should have talked faster. 5 days a week. Come on. Fit some math in, right? I mean, come on. I digress. But yes, we'll talk more about these because apparently nobody knows what cosh and sinh are, except somebody knows.
He said that they were the opposite.
I think he said sinh equals cosh. Yeah, that's all.
That's all.
He said sinh equals cosh?
What? The
integral of it.
Oh, the integral. Okay. Okay. You know us math people, we're very literal, right? Like you're like the spirit of it, they're equal, right? But there's an important detail there, which is the derivative or the integral of cosh or sinh is the other. Yeah. Okay, anyway, no minus. Cosh and sinh, just differentiate, integrate back and forth. We'll talk more about that. So integral of secant squared is tangent, right? Because the derivative of a tangent is what? Secant squared. How do you know that? How would you derive it? Memorize it is incorrect. But yes, it should be. I mean, you should have it hardwired by now. It should be in your memory. But if you forget, there is a simple thing you can do, which is differentiate sine over cosine, right? You use the quotient rule, which says that this is d dx of sine times cosine minus so this is the quotient rule, right? And so that gives us cosine squared x plus sine squared x, which is otherwise known as what? 1, right? So we get 1 over cosine squared x, which is secant squared, right? So this is not something that just needs to be memorized. It's something that should be understood, all right? But yes, you shouldn't have to go through that. You should know that. True, fair enough. The integral of cosecant squared is minus cotangent plus a constant. Very good. The minus is because it's the co-function, right? When you go through the quotient rule, you pick up a minus sine squared minus cosine squared rather than a plus sine squared cosine squared like we just did. Integral of secant tangent is secant x plus a constant. Very good. The integral of dx over 1 plus x squared is, oh, no. So this suggests to me that you're like trying to memorize stuff off the back cover of a book or something, which is, I mean, So, I mean, what I just erased is correct if a is equal to 1. But you didn't tell me a is equal to 1, right? So this is simply inverse tangent. And let's talk about why that is. All right? Let's talk about why that is inverse tangent plus a constant. And down here I've got inverse sine plus a constant. Very good. Right? I mean, it's fine for you guys. If I start writing calculations like that on the board, if you're sitting in the back, you should be like, hey, I can't see that, right? But that's fine for you guys. It's not your responsibility to write things for the class. Like, this is fine. But this brings up a larger point, which is when you can't see something or don't understand something, you should like raise your hand, ask me about it. You know, this is your class. You can ask questions. This is not an online class, right? You get feedback, real time, so forth. And integral of cosine squared and sine squared remain mysteries to us at the moment. So I guess we better learn how to do those. Very good. Here we've got integral of x sine x squared. I got a minus. No, not quite right. And no, well, well, this one, so the one that's right, I don't see very, the one that's correct, I don't see work for. This one's, I think this got the right answer, but the work here is like not what I'd like to see. Let me just go ahead and work these, okay? So like the top one, I I'll just work it over here. Integral of x, the sine of x squared dx. So this is something we should already know how to do from Calculus 1 because this is a pretty standard u substitution problem. So you should state the u clearly and off to the side perhaps. U equals x squared. Then that gives me that du is 2x dx. So making that substitution, I can also solve this for x. X dx is what? It's du over 2, right? So with that substitution in mind, I can take this x dx and make it a du over 2, which is 1/2 the integral of the sine of u du, which is 1/2 cosine of u plus a constant. Is wrong? Why? Yeah?
Because u is equal to x squared.
That's part of why it's wrong. It's not the final answer, right? But yeah, it's minus, right? There's a minus. So exactly, if I differentiate this, now I get back there. Without the minus, I don't. And so I have minus 1/2. And then what the gentleman in the front was saying, absolutely correct. I need to put back. I want an answer in terms of x, right? Not in terms of u. Leaving an answer in terms of u that's a less serious error to me than the minus in some sense. I mean, it's a sin of omission, not commission, I guess. I don't know. And then here, how would you do the other one? Integral of x cubed e to the x to the fourth dx. So I would put u equal x to the fourth. That makes my du 4x cubed dx. So now you can do this different ways. Like this is integral of x cubed e to the u, and dx is what? Maybe you were taught to do them this way, right? You just like solve for dx and plug it in. Were you guys taught that way? Some people say that writing that is wrong. I'm not such a person. I'm open to writing expressions that are hybrid, that have both x and u in it, with the understanding that we're going to simplify it, right? If it's a good u substitution, the x's cancel out, right? So this is a good u substitution because the x cubes, they cancel, and we're left with 1/4 e to the, well, u is what? X to the fourth plus a constant, which is what you got. So congratulations. Very good. But I do need to see proper notation for integration in here, right? Something like that. Yeah? And this one, so this one here, what's really missing is just u equals e to the x, right? So du is what? E to the x dx. So if you look at that, you can identify what's going on, which is that, I don't have a marker. Aw, man. Huh. Not sure these are working markers. Where was I? Oh, yes. So sometimes I use notation like this. Like this is my du, and of course this is sine of u, right? Something like that. But I mean, there's different strategies for expressing your work, but you do need to express the work and explain what you're doing. Use equality where there should be equality. Don't leave. Don't have floating expressions like at the start. I was looking at floating expressions. They're just like pew pew pew. There's no equality connecting the ideas. All right, which isn't to say that everything is connected with equality, right? Sometimes we make other kinds of steps, and there's not an equality which connects things. All right, well, with that, I'm going to go back to the start of Calculus 1 and just start hitting on some things that we may not remember. I will get back to the inverse tangent here before too long, all right? So let's just talk about algebra. What do we need to know about algebra? I would say the main example that slips through the cracks is completing this square. So if I had x squared plus 4x plus 6 equals to 0, how would you complete the square on this? What does completing the square do for you? So I take half of the middle coefficient, right, which in this case is 4. So I get x plus 2. I square that. And if I do that, what would happen if I actually FOILed that out? What would I have? I'd have x squared plus 4x plus 4, right? What do I have on the board right now? X squared plus 4x plus 6. What am I missing? 2, right? So I have to add 2. That's completing the square. All right, it's rewriting a quadratic expression so that the variable is inside a square. Right? Just like that. And the reason that we do this is so we could solve it, right? I mean, this is x plus 2 squared equals to minus 2. And then it happens that that means that x plus 2 is equal to plus or minus the square root of minus 2. In short, the solution is minus 2 plus or minus, by the way, we can rewrite that as plus or minus the square root of minus 1 times the square root of 2, otherwise known as plus or minus I times the square root of 2. So we get minus 2 plus or minus I times root 2, right? Now, it is a fortunate quirk of complex numbers that this taking a square and replacing it with plus or minus the square root still makes sense even when the thing inside the radical is a negative number. It just so happens that the structure of complex numbers makes this calculation make sense. All right? Now, what I wrote at the end is also what you should find if you do what? If you just have memorized the quadratic formula, right? So completing the square is how we derive the quadratic formula. But completing the square is important because this manipulation to a quadratic is an important thing that we need to do in order to solve integrals, all right? Let's do another completing the square just before we leave this topic. So I'm not even going to look at it as an equation. Completing the square is something we can do to a quadratic expression, right? You don't have to set it equal to 0. It's a quadratic polynomial, right? This is an object which exists on its own right, right? So here we have what? X plus 3 squared. What would 3 squared is 9, right? So I already have a 27. 27 minus 9 is 18, right? So there you go. Let me give you another example because I didn't like the way that one turned out. How about x squared plus 4x plus 3? Let's complete the square on this. By the way, if the x squared term had a number next to it, that kind of throws a wrinkle in your plans, right? But if you think about it, you can always just factor that number out and do what I'm doing if you wanted to do it that way, right? You can always manipulate your expression so that you have x squared as the leading term. Here, I'll do that here. Suppose I had 2x squared plus 8x plus 6. Ooh, right? So factor the 2 out, yeah? So if you have something like this, it's nice to put an arrow like that. All right, now we can complete the square. This is what, x plus 2, quantity squared. I heard minus 1, right? Very good. Because 3 minus 4 is minus 1. So there's a very big difference between this third example and the previous two, right? The previous two, after we completed the square, what happened? We had a plus, right? So if we look at that as a polynomial set equal to 0, what are the kind of solutions we get? Complex solutions, right? If you were to look at y equals to that quadratic, it wouldn't cross the x-axis, right? This, on the other hand, crosses, if I was set y equals to 2x squared plus 8x plus 6, where would that cross the x-axis, the graph of it? By the way, can you think of another way to look at this quadratic? I mean, I completed the square because that's kind of the thing I'm talking to you about right now, but come on, if I said simplify this quadratic, you would not complete the square left to your own devices, would you? What would you do? You'd factor it, right? And I probably would too. How do you factor this? X plus 1 times x plus 3, right? So what are the x-intercepts? -1 and -3, right? Very good. I can't trick you guys. How do you get directly from the completing the square to the factoring? Like, what's the difference? What's going on there? What's the general pattern? The general pattern is something like this, all right? We have something like x minus alpha, quantity squared, minus beta squared. If it's one of these with a negative, right? And so if you look at that, it's the difference of squares. So difference of squares, it's x minus alpha minus beta times x minus alpha plus beta. If it's a plus beta squared and beta is real, then an imaginary number I comes into play. Right? All right, so let me just take a second to do that, if I can find my red pen. So hopefully I'm not telling you anything new here. A quadratic does what? So this I could look at a different way, right? I'll do it up here. I could look at this as x plus 2 quantity squared minus 2i, well, excuse me, minus the square root of 2 I quantity squared, right? And then that's the difference of perfect squares, which means I can factor this as x plus 2 minus I root 2 times x plus 2 plus I root 2. To every pair of zeros for a quadratic, there corresponds a factorization, and vice versa, right? Now, those factors could be complex, right? So if they're complex, then we say that that polynomial is irreducible or prime as a real polynomial, right? It doesn't permit a real factorization. This sometimes happens, but the good news is every quadratic can be factored either into a pair of real factors or a pair of complex factors. What else do we know about the complex factors? They always come in conjugate pairs, right? So if I take the complex conjugate of one, I get the other, right? All right. Well, there you go. That's about everything I know about quadratics. So let's go on. What if I asked you to solve 2x squared plus 8x plus 6 greater than 0? How would you solve that quadratic inequality? What's the strategy for solving inequalities, by the way? Factoring is a good idea. So this is, we just did that, right? This is 2 times x plus 1 times x plus 3. And we learned some things in Calculus 1 about continuity, right? For example, one of the things you should have learned about is that if a function changes from what? From positive to negative, and it's a continuous function, what has to happen between where it was positive and where it was negative? It has to cross the x-axis, right? It has to have hit 0 somewhere in there, right? Moreover, it can only change from positive to negative where? Where there's a 0, right? Or where the function's undefined. Or where it has a discontinuity, perhaps. Now, this is a quadratic, so it's everywhere continuous, right? So to decide whether this is positive or negative, all we need to do is make a number line and put the places where it's 0. And then we just have to think about cases between those zeros. That will completely nail down where this thing is positive and where it's negative, right? And this strategy will work for other functions. If you can identify where the function's continuous, right, where it has zeros, so you just need to look for zeros, for points of discontinuity, and for places where the function's not defined. If you take into account all those so-called critical points, not in the sense of maximization or optimization last semester, but in the sense of sign, like plus or minus, then you can make a sign chart and solve the inequality for the function, right? That's what we're doing. Here, I'll do it. So here's my number line. Now, I'm not sure Dr. Sprano did it this way, and different people have different ways of organizing this, but here's how I do it. Number line, 2 times x plus 1 times x plus 3. And great, so if you plug in any sample point over here, for example, 0, you get positive. If I plug in anything between -1 and -3, I get negative. And over here, I get positive again, right? None of this is surprising because, of course, you guys realize that the graph of this function is this, right? So, of course, it's negative between the x-intercepts, and it's positive to the side. So what's the solution to the inequality? Solution set. It is -infinity to -1 not included, unioned with -3 to infinity included. This is interval notation. Bless you. Yep. What? Oh, yes, thank you. Sadness. I mean, just as I planned, right? For your learning. Yes, in fact, -3 is smaller than -1. This is a thing my 10-year-old's currently struggling with. Apparently, I still struggle with it. But yeah, that does matter. Thank you, sir. Hey, let's make another modification to the problem. What happens if I throw in equality? How would that change the problem? What if I threw in equals here and here? What would that change? Yeah. Yes, very good. We have to include, which we use square bracket to include, right? A related problem, right? If I was to solve, let's say, 1 over 2x squared plus 8x plus 6 to be greater than or equal to 0, what would the solution there look like? It's actually the same, right? It's just now instead of the places which were critical being zeros for the function in question, they're just places where we have division by 0, right? So those are points that are outside the domain of the expression. So we go back to my original solution set because x equals to -3 and x equals to -1 are not allowed. Those give division by 0, right? They don't give 0. So in fact, solution set here, x is an element of -infinity to -3 not included, union with -1 to infinity, like that. This notation, if you've had Dr. Sprano, I'm sure you've heard this before, this means element of, right? Elementary, you learn how to spell element of. Right? And this u here is a union. If I erased the greater than, right, and if I just said solve this, solve 1 over 2x squared plus 8x plus 6 equals to 0, what's the answer? Right, there is no solution. There's no way you can get 0 from a fraction whose numerator is never 0, right? So there's a kind of meta comment for you. If you're solving a fraction, right, the only way to get 0 from a fraction is to make the numerator 0, right? Now, if the numerator to a fraction is 0, that doesn't mean that the fraction actually gives you 0, because what could happen? The denominator could also be 0, right? It could be a place where the fraction is strictly speaking undefined, then we need limits and so forth to discuss that kind of problem. All right, anyway, enough about algebra. That's the start. We'll be doing algebra the rest of the semester, though, so I wanted to get the ball rolling here with that. So what came after algebra? Of course, we like to talk about calculus, right? And so in particular, I would remind you, f prime of a is the limit as h goes to 0 of f of a plus h minus f of a over h, right? This does what? This defines the slope to the tangent line if it exists, right? So if I was to graph this, suppose that that's the point. Can you guys tell me what the significance of f prime of a is there? Is it positive? Is it negative? What's the deal? F prime positive or negative at this point? Positive, right? How do you know that? Ow. Yeah, because the slope is positive, right? I mean, and what you mean by that is if I was to draw a tangent line here, right? Try to draw a tangent line. This is positive slope, right? Positive slope. What's the equation for that tangent line? What's the equation for the blue line? What's its point of tangency? This point right here is by assumption a comma f of a, right? So if I want to write an equation for a line that goes to the point a comma f of a and has slope f prime of a, the answer to that is simply f of a plus f prime of a times x minus a. That right there, by definition, is the equation to the tangent line if it exists. It doesn't have to exist, right? There are lots of functions which are not permitting a tangent line at a given point, right? Functions which are not differentiable. Can you guys tell me an example of a function which is not differentiable, at least at one point? Absolute value is a good example, right? So can you tell me a formula for absolute value? I mean, the case-wise is one thing you could say, tell me, right? Minus x, x less than or equal to 0, x if x is positive, right? Can you tell me an algebraic formula for the absolute value function, though? Anybody know? Fun fact, it's the square root of x squared. So if somebody asks you, is a function differentiable, you got to be aware that weird stuff can be hidden inside algebraic formulas, maybe ways you didn't realize. Getting back to my story here, this is the tangent line, right? Can you tell me what the name of the function is here? This is, we could give this function a name. If I could find a marker. Yeah. Thought I brought a red marker. Yeah? Oh, no. What's the name of this function in its own right? This is known as the linearization of f at a. Now, Dr. Sprano told me he didn't get a chance to work that into Calc 1 last semester. So there it is. If you replace a function with its linearization, that is basically saying, I'm going to trade the function for its tangent line. Right? So, for example, For an example of that, if we have f of x equals the sine of x, right? And what's f prime of x? It's cosine of x, right? It took us a while to derive that in Calculus 1, right? Like, there's a lot of details behind that. Those are last semester. I'm not going to go through them again here. But then there's a lot of daylight between here and here. There's like a couple hours discussion there. Anyway, it's true. And so if we look at the linearization at 0, what do we get? So if I must be a slave to my notation, I'm saying a is equal to 0. F of a would be sine of 0, which is what? A sine of 0 is 0. Very good. I like that that was told to me without thinking. I mean, that should be instinctual. If you have to plug that into your calculator, that's not good. We should know sine of 0 is 0 at this point. We should know that cosine of 0 is 1. Very good. Now, if you're like, I don't know that. How do these people in this class know that? Well, they have a distinct advantage over you. They have studied Calculus 1. And that might not be fair, but life is not fair. It's true. I think a good saying is anyone who says differently is probably selling something, right? This is a time-honored saying. It's a good saying. It has merit. Are any of you multi-level marketers? Do any of you know a multi-level marketer? Do you guys know what multi-level marketing is? It is like a pyramid scheme, right? Yes. Okay. Just checking. Friends don't let friends multi-level market, I think. Let's see here. Okay, so where was I? So I have a notation. The linearization of f at a of x is f of a plus f prime of a times x. This is just a notation. This is just name calling. And so what is that here? 0 plus what? 1 times x minus 0. It's kind of anticlimactic. We get x. So I could summarize this by another way of looking at this, aka sine of x is approximately x for x approximately 0. This is the linearization of sine by x. Now this is the start to a much longer story we're going to tell this semester, which is how do you do better than that? Like what if you want a quadratic or a cubic or a quartic or a quintic approximation to sine? How do you do that? We're going to learn how to do that in here. That's a large part of the story in here, is continuing the story of linearization to higher order polynomials. These are called Taylor polynomials, right? That's one direction we're going later. Oh, I'm sorry to bring one direction into this lecture. I don't try not to do that, but it just happens sometimes. But getting back to Calculus 1 again, let's talk about this inverse tangent, right? So differentiation, algebra. What are the rules of differentiation that you guys know? Derivative of a sum is the what? Sum of the derivatives, right? The derivative of a product is the product of the derivatives, right? Wrong. No, that is not true, right? There's this pesky thing called the product rule that we must take care to respect. All right? So rules of differentiation. And so, of course, 1, we have that f plus g prime is f prime plus g prime. 2, we have that a constant times a function is a constant times the function, right? This is the prime notation. 3, the product rule I was just mentioning, fg prime is f prime g plus fg prime, right? What if you have a product of 3 things? How do you do that? you know the triple product rule? It's this, f prime gh plus f g prime h plus f g h prime. This goes on. There's a general product rule called Leibniz rule, but we don't need to get into that right now. There's lots that are known about derivatives. I used the quotient rule a little bit earlier today. I won't write it down again. You guys know it. But there's another thing that goes on, which is important, which is f composed with g prime, right? And here, I can't get away with not writing of x. I got to write of x to be clear. F composed with g prime of x is what? It's f prime of g of x times g prime of x. This is the chain rule, right? The thing that vexes many calculus students. Another way to write this, d dx of f of u of x is df du times du dx. This is another way to write the chain rule, all right? Now, the chain rule is important because it's a lot of what makes implicit differentiation work, right? Do you guys remember implicit differentiation? What's the idea of implicit differentiation? Suppose I had like x squared plus 2xy plus y squared equals to 7. What'd I do? Feel free to interrupt.
Differentiate both sides with respect to x.
Yes, differentiate both sides with respect to x. But what's the fussy point? We have to think of y as being a what?
It's not like a function, it's like creating a relation or whatever.
We're creating a relation. I'll agree.
Y is its own variable that
Y is some function of x, right? Yeah, it's its own variable. Sure, I'll buy into that. Now, when you do this, you're using a theorem of advanced calculus, which says that there exists a way to solve y in terms of x as a function, right? In fact, that can only be done locally, given certain conditions on the equation. But, you know, we don't burden Calculus 1 students with that. We just say, you implicitly differentiate. And hopefully you don't get into trouble, right? And usually you don't. So here we go, 2x. And then this is d dx of what? 2xy plus d dx of what? Y squared equals, what's the derivative of 7? 0, right? And then expanding this, we have 2x plus, what, 2y plus 2x dy dx plus 2y dy dx equals to 0, right? Yeah. And then you can solve this for dy dx, right? This is pretty typical implicit differentiation problem, right? Okay. Now, what does that have to do with this inverse tangent I was talking about earlier today? How do you find the derivative of inverse tangent? There are two ways. The one is to derive an algebraic expression for inverse tangent in terms of the natural log of an algebraic function. How many of you can tell me what the formula for inverse tangent is in terms of the natural log of, maybe that doesn't even work for inverse tangent actually. I may be thinking an inverse hyperbolic tangent at the moment, but here's how you do it. So if I want to solve the derivative of inverse tangent, and this will be it for today, right? Let me remind you how we do this, just in case you forgot. This is y equals to inverse tangent of x. So I give a name to what I'm trying to differentiate, and then I take the tangent of both sides. All right. So this gives me tangent of y is tangent. What's the tangent of inverse tangent? It's just x again, right? So we have x. Now what? Now implicitly differentiate. With respect to x. this gives me secant squared y dy dx is equal to 1. And then I can, well, dy dx is what I'm after, right? So I solve for dy dx, which is 1 over secant squared y rather, right? But what can you tell me about secant squared y and tangent squared y? What relation do we know? We know that sine squared y plus cosine squared y is 1, right? So if you divide that relation by cosine squared, what does it give us? We get tangent squared plus 1 is secant squared y. This is an identity which is known for tangent and secant. You could call it the Pythagorean identity if you wanted, whatever. The larger point here is that secant squared y is what actually, it's actually 1 over tangent squared y plus 1, which, hey, what does this tell us? This tells us that d dx of inverse tangent x is 1 over 1 plus x squared. And so that's how we can understand where that's coming from. Right? Now, yes, you can also memorize it. I'm not stopping you. But we can understand this from more basic principles. It's not that hard. You can derive the derivative for inverse sine much the same. So tomorrow, what I'll do is I'll continue talking about sine and cosine. We'll get back to like the sine squared and cosine squared probably. And I'll try to talk about hyperbolic functions and all that tomorrow. And then I'll try to get back on track with the course planner here pretty soon. It'll be a little while till we get to the integration techniques. So if you talk to people in other sections, they're going to be doing integration by parts right now. We're going to get to that. It's not right away. Thanks, guys. Oh, I'll get it.